Hello. Today we're going to talk about signals and the speed of information and what the implications of this speed are. Here's a disclaimer. The material is based on sound scientific principles. The opinions expressed here are mine based on the observations we are going to make. This presentation has not been peer-reviewed or accepted by any journal. The information in this presentation is general in nature and not intended as professional guidance, nor will it assist you in passing any exams. You're encouraged to confirm any information obtained from this presentation with other sources, and this material is copyrighted. This presentation will discuss the speed of information, how long a signal takes to reach us, and what the repercussions of that are. Then a case study will be presented to illustrate the points that we will make. Based on what we will learn, we will discuss the meanings of these concepts in terms of fate and determinism, a practical definition of the multiverse, time travel, and the Pauli exclusion principle. We're made of the world around us through our senses: sight, hearing, smell, touch, and taste. These senses, when activated, help us understand the world around us. But we will focus on light and sound, since these allow us to perceive information at a distance. All signals take time to reach us, but most travel so fast that they seem instantaneous. Light can travel a foot in a nanosecond, and sound through air can travel that far in a millisecond. In the following, we will use analogies involving sound, but they could just as easily be applied to light. The primary difference is that because of the speed of light is so much faster, the distance and times would be much larger. I find these analogies using sound are more relatable to everyday events, and that's really what we are striving for here. We will introduce a governing equation so that we might understand how signals move over time. The most common form for how signals move is a function of omega times t minus k times r, with the amplitude decreasing by r. The function f describes the signal as it leaves the source. The signal might be a voice communication, a video signal, or digital data as a series of pulses that vary over time. The constant relates some aspect of the signal, such as a moment at the beginning, middle, or end of the signal. In this expression, omega is the radial frequency of the signal, and t is the time. This product relates how the signal varies over time at any point in space. K is the wave number and r is the radial distance from the source. This product relates how the signal varies throughout space at any instant in time. The signal decreases in amplitude with distance from the source. We can relate frequency and wave number by the velocity of the signal as shown. We can then relate the distance that the signal has traveled at any given time. We see that the signal moves uniformly outward from the source with time. From a point source, a signal moves out uniformly as a sphere. Now we will provide an example showing how signals take time to reach us and what effect this might have. We will show that the same event can be seen differently by each observer. In this case study, let's say that there are two clock towers that are a mile apart, and that three friends, our observers, live between the two towers. The three friends meet the next day to discuss what they heard. We note that the time of arrival and amplitude or loudness are measured to be different by each observer. The observations are dependent on the distance each observer is from the source. Let's name the clock tower to the left as red. The red signal is heard sooner by the closest and later by the furthest observer. The top chart shows an animation of how the signal moves from left to right across each observer. The bottom chart shows time when each observer hears the red signal. The height of each line represents the loudness of the signal by each observer. Specifically, the order that each observer hears the red signal is as follows. Number 1 hears the signal, then number 3 hears the signal, and then number 2 hears the signal. Now let's show the other clock tower to the right, which we will call the blue tower. The meaning of each chart is the same as the previous slide. Again, the loudness decreases with distance. The order of the signals and their amplitude are different than in the previous slide. The order that each observer hears the blue signal is as follows. Number 2 hears the signal, then number 3 hears the signal, then number 1 hears the signal. Now let's overlay these two signals. Let's say these two towers chime at the same time. Events are perceived differently by each observer. Number 1 hears red, then blue, spread very far apart. Number 2 hears blue, then red, but a bit closer together. Number 3 hears blue and red at almost the same time and loudness. We have shown the time it takes a signal to reach us affects our perception of the events, specifically their order and amplitude. The time we perceive an event is dependent on our distance, whether that be sound, light, or radio. So how do we make sense of this? Which observer is right? Well, they each reported exactly what they heard, and accurately. We might say that objectively, they each heard two chimes from two towers that are in opposite directions. But subjectively, they each experienced the order and loudness of each chime differently because it took time for the sound to travel. The lower plots presented might represent a space-time chart, but that does not really help us understand the underlying phenomena. So who's right? Well, they're all right, each and every one of them. We might be comforted to know that this time difference of arrival has many uses, one of which is determining our location. By measuring the time difference between sources that have known locations, we can triangulate our position quite accurately. GPS, Galileo, and other satellite systems all use this technique today. I once had a discussion with a university physics professor. She taught a course in special relativity. I stated that this was a trick of the light or a distortion, and she got agitated and stated that my observations are my reality. Even though I understood her point of view, I didn't agree with it, but I let it go. My point is, how can we make sense of the world if we accept our observations without understanding the underlying processes? From our top-down view, we saw that both chimes happened at the same time, but not all our observers saw it that way. How do we perform a consensus unless we can peek behind the curtain? Well, that is really all there is to learn in this video. The remainder of this video will discuss deeper thoughts based on these ideas. So by the time we are made aware of an event, it's already happened or is happening now. Does that mean that our fate has already been determined? I don't think so. Your past experiences will influence your future decisions, but if you don't like the path that you're on, you can always change lanes. We should always strive to be the best version of ourselves, and we should also strive to help others live their best lives too. While we may not know all of the initial conditions, to some extent we can predict the future based on our experience and our observations to date. We must learn and be smart. We can see what's coming and decide how to react. Not that many events happen so fast that we cannot avoid them. So stay alert and be resilient. In this presentation, we saw that each observer experienced events differently. It's fun to think that there are different versions of us doing things differently, a multiverse. The reality is that we all live in this world, the same world, even though we experience it differently. To recap, objectively all observers heard both bells, but subjectively they heard them in different order and loudness. And besides, an infinite multiverse would violate the principles of the conservation of mass and energy, requiring infinite amounts of both. I don't see that being very practical. So here's my definition of the multiverse. We each live at the center of our own universe, kind of like the philosophy was thousands of years ago, or even hundreds of years ago. In general, information travels fast and often reaches all of us at the same time. This allows us to have many shared experiences of the world around us. This slide has to do with the possibility of time travel, and I base it on the Pauli exclusion principle, which states that two or more identical particles with half-integer spins, such as fermions, cannot occupy the same quantum state within a quantum system simultaneously. I interpret this to mean that two particles cannot occupy the same coordinates at the same time. Alternatively, I would propose a corollary that says that no particle can occupy more than one coordinate at the same time, which implies that time is universal and unbendable, that there's only one solution to the equation of the universe, if you will. It would be easier to bend ourselves than this fundamental concept, and this somewhat ties back to determinism again. So, to recap, all information is made in the past. Signals take time to reach us, depending on distance, and we can see all the same events, but not necessarily in the same order. If you found this presentation interesting and/or informative, please like and subscribe.